Rotational kinetic energy. After kinematics and dynamics were covered, your physics education continued with the concept of energy. Energy is hard to define, but since it's a scalar quantity, it's great for solving problems. By now, you should be ready for the concept of a rotational version of the translational kinetic energy. Given that kinetic energy equals 1/2 mv squared, what substitution should be made? All right, first we start with our equation for kinetic energy, translational, so it's 1/2 mv squared. Then we're going to use the rotational equivalent of velocity, so v equals r omega. We're going to substitute it into this equation. This here is the kinetic energy of just one small piece of the entire rigid rotating body. So this is the mass of that piece, this is the distance between that piece and the axis of rotation, this is the angular velocity. Why is there no subscript? Because all of the pieces of a rotating rigid body have the same rotational velocity. So we don't need the subscript. Then we're going to square this and we get this expression. Next, we add up all the kinetic energy of all of the little pieces. So we have 1/2 mr squared omega squared for the first piece, 1/2 m2 r2 squared omega squared for the second piece, etc. We can actually factor out that omega squared since it doesn't have a subscript. It's the same for each term in this equation. And what do we get? We get a summation of the mr squared for each piece of the mass, each piece of the object. And what is this? By definition, this is moment of inertia, right? The summation of mr squared of every piece of that object is the moment of inertia. So we get our new equation for rotational kinetic energy, 1/2 I omega squared. The concept of work was introduced in parallel with energy, where work equals force times displacement. A shortcut will now be taken to determine how much work is done by an applied torque. The rotational equivalents of force and displacement will just be substituted into the above equation. Work equals torque times angular displacement. What fell out of the original work equation and why? The angular nature of the equation. Torque is, by definition, always perpendicular to the angular displacement, so sine theta equals 1, and work is the product of their amplitudes, so we don't need the sine theta in this rotational version. This course has so far discussed 3 types of energy: gravitational potential energy, kinetic energy, and elastic potential energy. All 3 of those were dealt with in terms of a point mass. There was no rotation. Now that we have rigid rotating bodies, kinetic energy will be redefined as a total kinetic energy that sums up the translational and rotational aspects. A common problem in rotational motion is having 2 different objects, each with the same mass, and determining which will get to the bottom of an incline first. If they were just blocks or even spheres that slid down without rotating, they would get to the bottom at the same time, since objects fall at the same rate. By using an extended mass, not a point particle, and rotation, it's quite different. Why? Think about energy. At the top of the ramp, both objects have the same potential energy. How about at the bottom? For a non-rotating object, all of the gravitational potential energy is transferred into translational kinetic energy. If the object rotates, then part of that energy, that initial energy, goes into rotational kinetic energy. Rotational kinetic energy depends on the shape of the object, which affects the moment of inertia. A sphere and a hoop of the same mass and radius both start at rest at the top of a ramp. Assume that both objects roll without slipping. Which one gets to the bottom first? Here's the sketch. What is the equation using the conservation of energy that will give the velocity of the objects at the bottom of the ramp? Solve the equation. Qualitatively, how can that be used to determine which object reaches the bottom first? Try working this in your groups before going to the next slide. So initially, when the hoop is at the top of the ramp not moving, it only has gravitational potential energy. At the very bottom, it's going to be rolling and translationally moving at the same time. So it's going to have two forms of kinetic energy, translational and rotational. Therefore, you can do this equation for each of these objects, right? This equation right here is just for one of the two objects. Now, gravitational potential energy is mgh. Kinetic energy translational is 1/2 mv squared. And here we have our new rotational kinetic energy, 1/2 I omega squared. So you're going to have this equation for the hoop, and then you're going to write it again over here for the sphere. And you're going to solve each one for v and see which v is larger, because this v is translational velocity. So whichever one is moving the fastest down the ramp is going to win the race, right? So we're trying to see who has the largest velocity v. Did you question why it was stated that the sphere and the hoop were rolling without slipping? Well, when that occurs, rolling without slipping, then this equation is true. Velocity equals r omega. There is a correlation between how quickly the object is rotating and how quickly it's then rolling down the hill. There's a correlation. You can calculate how far it's going to roll down the hill based on like the circumference of the circle and how fast it's spinning. You can calculate velocity. So this equation is only true when there's no slipping. And therefore, we can solve this equation for omega, v over r, plug that in here, and get rid of one of the unknowns. If an object is sliding, so imagine this hoop was sliding without rotating, then this equation isn't true. Think of a car on an icy road. The driver slams on the brakes. What happens? The wheels lock up, and the car wheels slip on the road. So here's the ice, here's your tire, and it just slides without rotating. Therefore, the wheels have a translational velocity, v. However, the angular velocity of the wheels is 0. So clearly, v does not equal r omega. Imagine your car gets stuck in a sand dune. The wheels are spinning fast, but the car isn't going anywhere. If there's no correlation between the speed of the tires spinning and the distance the car is traveling down the road, then this equation is not true. V does not equal r omega. So back to the initial problem, where the substitution omega equals v over r will be made in the rotational kinetic energy expression. All right, so both the hoop and the sphere start out with that same conservation of energy equation. We're immediately going to replace omega with v over r for both of them. However, what is different here is that the moment of inertia for the hoop is mr squared, while the moment of inertia for the solid sphere is 2/5 mr squared. So that's the difference between these two equations, is just the moment of inertia. Next, we do a bunch of algebra, and we simplify this expression and solve it for v. So look, each term has an m. They can all go. And we have r squared. And look, we also have r squared here. So that r squared is going to cancel with that one. And therefore, we have 1/2 v squared plus 1/2 v squared, which is just v squared. And, oh, they got rid of the 1/2 by multiplying the whole thing by 2. So if you multiply this whole equation by 2, then that becomes a 1 and a 1. So you get 1v squared plus 1v squared, which is 2v squared over here. And then divide both sides by 2. And then finally take the square root, and you get the square root of gh. Over here, we had that 2/5. So look, those 2's cancel, and we're left with 1/5. Now there is still an m in every term, so you can get rid of the m. This r squared still cancels with that one. But now we have, we're going to multiply the whole thing by 2. So that becomes a 1, and this becomes 2/5. So we have 2gh equals v squared plus 2/5 v squared. So what is 2/5 v squared plus 1 v squared, or 5/5 v squared, becomes 7/5 v squared.
We're solving for v. So we're going to multiply this side over here by 5 over 7, which is the same thing as dividing by 7/5. Therefore, we get 10 over 7 GH. And on this side, we're going to have v squared. So we're going to take the square root, and we get 1.2 times the square root of GH. So this answer was GH. That's the speed, the velocity. This one is 1.2 times that. Therefore, the sphere reaches the bottom first because it is traveling translationally, linearly, it is traveling faster. The velocity of the sphere is 1.2 times as much as the velocity of the hoop. Did that surprise you? Qualitatively, that means that the sphere gets to the bottom of the ramp first, because at any point on the incline, the sphere has a greater linear velocity. Solving the kinematics equations would give you the same answer. One more question. Why did this happen? Both the sphere and the hoop started with the same gravitational potential energy, and at the bottom of the ramp, both had 0 gravitational potential energy and a maximum kinetic energy. Again, both the same. But the hoop, with its greater moment of inertia, took a greater amount of the total kinetic energy to make it rotate. So there was less kinetic energy available for translational motion. So because this has a greater moment of inertia, it requires more energy just to get it to roll. Hence, the sphere has a greater translational velocity than the hoop and reaches the bottom first. If your GPE equals your translational kinetic energy plus your rotational kinetic energy, the bigger this is, the lower that has to be, right? If they both start out with the same GPE, so that's constant. Therefore, the more difficult it is to get something to roll, the slower it's going to move down the ramp. A cylinder with a moment of inertia of 1/2 mr squared and a hollow sphere with a moment of inertia of 2/3 mr squared have identical masses, radii, and initial linear velocities while rolling without slipping on a horizontal surface. Derive the expressions for the maximum height that can be reached by each object as they enter the bottom of the same inclined plane. How would you compare your results? All right, so we start out with the same conservation of energy equation as before. The initial energy of the object must be equal to the final energy. Initially, the objects are rolling with translational velocity, so they have both forms of kinetic energy, and at the end, all of that energy is going to be converted into gravitational potential energy. So the only difference down here is the moment of inertia of each object. When you simplify the algebra, you get that the hollow sphere will end up higher up on the ramp than the cylinder, because 5/6 is greater than 3/4. Why does this happen? Well, because the hollow sphere has a higher moment of inertia, it's harder to get it to roll. So the fact that this sphere is rolling with the same velocity as the cylinder means that there must be more energy in the system for the hollow sphere. So therefore, that energy, that extra energy that is in the system that allows both of these to have the same initial velocity, that's going to let it go higher up on the ramp because there must be more total energy in the sphere than the cylinder. A disk with a mass of 12.5 kilograms and radius of 0.5 meters is mounted on a fixed frictionless axle. An external force increases the disk's angular velocity from 0 to 26.4 radians per second over a time span of 3.2 seconds. What is the average power input to the disk during this time? The moment of inertia of the disk is 1/2 mr squared. Power is defined as change in energy over time, where work is torque times theta. However, we aren't given the force or the torque in this problem, so we're going to use the fact that power is the change in energy over time. Now, the only type of energy that this object has is rotational kinetic energy. So the change in rotational kinetic energy is the final value minus the initial, but it starts out at 0 velocity. Therefore, that goes away. This 2 moves to the bottom, And we have this equation, I omega squared over 2t. Now, I is 1/2 mr squared. So 1/2 mr squared, that 1/2, that 2 got moved down here, and therefore that 2 becomes a 4. We have omega squared over t. If you plug in all your numbers, you get 170 watts.